Section 8.1, Exploring Exponential Models. In this section, we're going to talk about exponential growth and exponential decay and exponential functions in general. So to start off, we need to identify what makes an exponential function. We've had, all the way back from the beginning of the year, we've had linear equations, we've had quadratic equations, we've had cubic functions and quartic functions and all types of different functions. But one thing we haven't had so far is when we have a type of function where our exponent is actually the variable part of our equation. So if you look up here at my exponential function, you'll notice that I have two values here that are constant, while my exponent is the part of my function that I'm going to use to put in my independent variable, calculate values. So this exponent up here is going to constantly change. So this graph does not look like a line. It doesn't look like a parabola. It has its own unique shape when we graph it because the exponent is constantly changing. Now, two things when we work with exponential functions. You either have a growth function or a decay function, meaning the function is either increasing or it is decreasing. In an increasing function, a growth function, your b value here, this number that goes with the exponent itself, has to be greater than 1. So when you look at b and you see a number greater than 1, you know this function is going to be increasing. So as I go from left to right on my graph, you're going to see this curve getting bigger and bigger and bigger and bigger. Now, the opposite side of that is a decay function. And when you have a decay function, you'll notice it says that my b value needs to be between 0 and 1. And there's a very specific reason why we don't use 0 and 1 in these functions, and I'll talk about that here in just a minute. So you'll notice in this particular example, my b value is 0.25, which is definitely a value that falls between 0 and 1. So if I were to be looking at this graph, as I move from left to right on my graph, I'm going to see values that start higher and then work their way down as it goes off to the right. Okay. Now, the reasons we don't use 0 and 1, first of all, if you think about it, if you put the number 0 or you put the number 1 right here, where you're going to take it to a power, 0 to any power is always going to be 0, and 0 times anything is always 0. So if I put 0 in there, my function is never going to do anything but be 0. Same thing kind of happens when I put in a 1. If I put in a 1, it doesn't grow, but it doesn't get any smaller, because when I put in 1, 1 to any power is still going to be 1, and 1 times a number is always going to still equal that same number. So like in my example here with 300, if there was a 1 here, 1 to any power, no matter what I take it to, is going to be 1. So no matter how far I go left or how far I go right on my graph, I'm still going to be at 300. So in other words, 1 is going to give me no change at all, and 0 is going to give me everything to be 0. All right, so it's really easy to quickly determine from the function itself whether it's showing growth or decay, which helps before you graph it to kind of know which direction the graph is going to go. So like in my examples that I have right here, the first one, I have a b value of 1/2. And if I have a b value of 1/2, that's going to tell me that my function is a decay function. In other words, this is going to be a decreasing function because b is between 0 and 1. Now, the second example, my b value happens to be 5, which is definitely greater than 1, and anything greater than 1 shows a growth to that function. Then next one, we'll just finish up these two real quick here. This one, you have 2/3. 2/3 is a value between 0 and 1, so that also shows decay. And then finally, the last example I have here, without graphing this on a graph, I can tell that this is growth because my b value is a positive 12. Okay, so I had two that show growth and two that show decay, so I could expect to know which way these graphs are going to go before I actually were to draw the graph or to put them on the graphing calculator. Now, one of the things that you're going to have to do is be able to take a situation that's being described to you, and whether it's growth or decay, and turn that into the actual function that needs to be used. And so to do that, you'll notice that my growth or decay factor is not necessarily the percentage of growth or the percent of the decay. So when we have to figure the actual factor itself, okay, so we're talking about the B value here, we're going to, regardless of whether it's growth or decay, we're going to start at 100%. Okay, if I keep 100% of something that I have, that means it doesn't change. It means it doesn't grow, but it means it doesn't get any less. So I just stay with the status quo. I keep everything the same. If I want something to grow, however, I need to add that growth. So if I have a growth of 5%, I'm going to start at 100, add 5%, gives me a total growth of 105%. Well, now we can't use that in our equation as a percent. Just like always when we calculate with percentages, we need to change it to a decimal. So for my actual B value, I'm going to use the decimal equivalent of 105%, which is 1.05. Now, decay is the same way. Remember I said if you stay at 100%, you're going to stay the same. You're going to stay level. We need this to decrease by 12.5%. So what I will do, if I have a decrease of 12.5%, again, I start at as 100. That's my even playing field there. And then if it's decreasing, I'm going to subtract the percentage by which it is decreasing. So in this case, it's decreasing at 12.5%, which leaves me an overall percentage of 87.5%. Now, as the decay factor in this case, B, if we change this to its decimal equivalent, is going to be the decimal 0.875, and that would be the number that I'd put into that function for B. Okay, and there's only two things we have to put in this function, right? It's y equals a times b to the x. So if I know B, the only other thing I need to know to put in that function is a. Okay, and a is actually a very simple number to find. Okay, we're going to use this one as an example to show you how we would set up this equation. And the first thing it asks us to do is to find the growth factor for that year. So we have these birds that were counted in a wildlife refuge and they in 2000, and it says they were about 1.2 million. And we have an average annual rate of increase of 0.5%. So I want to point out to you, we're talking about an increase. So we're finding a growth factor. We're not finding a decay. So just like we just finished up, I always start at 100%. And if I have a growth of 0.5%, I'm going to take 100 and I'm going to add 0.5%. So be careful on your decimals here. This comes out to be 100.5%. And a 100.5% as a decimal for my actual growth factor is 1.005. So when I make my function in the next part, I'm going to be using 1.005 for my B. Now, the next part does ask me to actually write the function. Okay, so I'm starting out with the generic y equals a times b to the x, and we already know what we're going to be using for b because we found that in the last part. The only other missing part is a. Okay, well, a is your multiplier here. This tells me what is the amount that I started with. How much did I originally have? And in this case, we're talking about the population of birds. So what was my starting population of birds? Okay, well, my starting population of birds was 1.2 million. So I'm going to start with, my function is going to say y equals 1.2, that's my a value, times, and I don't care if you use a time sign here or parentheses or something, you've got to put in here. And then my multiplier, I'll go ahead and do parentheses, I like that better. My multiplier that I found, or my growth factor I found earlier, was 1.005. And in this case, just to write the function, I'm going to put my x for my variable up there. Just like all my other equations, right? I've got to have x's and I got to have y's so that I have places to plug in my numbers and do my calculations. Okay, so this would be the appropriate function to model this situation. And then from this point, I could ask any person to tell me, you know, in the year 2005, what was the population if it continued to grow? So we would take the number 5 because that's 5 years that have passed, put that into our function for x and calculate that value, right? So you could calculate any year you wanted to now that you have this particular function. Now you can also do that with a depreciation type of situation. Okay, so this is talking about a car, and it says it costs $11,800 and the expected depreciation is 20% a year. And they want us to estimate the depreciated value of the car after 6 years. All right, so let's do that. First thing then, we're talking depreciation here. That means a decay. Depreciation means it's going down in value. So when I do that, I want to go ahead and come up with my B value, which is going to be a depreciation. So I start at 100%, and I actually subtract the depreciation of 20%, gives me a total of 80%. So for my B value, I'm going to use 0.8 or 0.80, right, if I convert that to a decimal. And then to write my actual function, the A value is the original value of the car, or at least from when I purchased it. And when I purchased it, it cost me $11,800. So I want to take $11,800 and I want to use that as my A value. Now, once I have that in, then I need to put in my B value, which I just already calculated. That B value is 0.8, and my X is my exponent. Now, for my specific problem, it wants me to predict in 6 years. So I will take my function and I will put in the exponent of 6. Okay, so we're going to go 11,800 times 0.8 to the 6th power. And according to this, in 6 years, that car will be worth $3,093 and approximately 30 cents. Okay. All right, so the last thing, we're going to write an exponential function using only 2 ordered pairs. And it all boils down to using this same format, y equals a times b to the x, to actually write that function. So here's how we're going to do it. We're going to start with the first ordered pair. We're going to plug that into our function. So y equals a times b to the x. So mine is 6 equals a times b to the first power, which is 6 times ab. And I'm actually going to solve that or get a by itself. So to do that, I'm just going to divide by b, and I get that 6 over b equals a. Okay, so far it doesn't seem like it's gotten us very far, but here's what we're going to do with that. Now that I have that, I'm going to use that along with my other ordered pair, and I'm going to do the same function again. So y, so 54, equals, now for a this time though, I just found that a is also equal to 6 over b. So I'm going to put that in for a, and I'm going to put b squared, because I'll put the 2 in for the x. Okay, so I did 2 things. I took the ordered pair 2, 54, put that in for xy, and I also took the thing that I just found for a, and I put it into a in this equation. What that does is give me all the same variables, so I can combine this together, and I end up with 54 equals, when I do this reducing here, b squared over b just makes this 6b. So then I solve for b by dividing by 6, and I get 9. So I know that b is 9. Now, once I know that b is 9, I can actually go back over here and figure out what a is. 6 over 9 is a, and 6 over 9 is 2/3. Okay, so now that I know that a is 2/3, let's put together our whole function. So y is 2/3 times 9 to the x. And there's my final function right there.